So I'm really pleased to introduce a really important scientist in plant nutrition for the last several decades, Paul Fixen, very much a leader in IPNI. IPNI has been connected to the Phosphorus Sustainability Research Coordination Network since we got started, and subsequently to that to the Phosphorus Alliance, and we've been very pleased to have that connection. And today we're sort of solidifying that with Paul to give us reflections on many of these topics we're talking about today. We're really lucky that he's able to join us. So Paul, take it away.
All right. I'm going to get rid of that picture as soon as I can. Well, am I on? Are we doing all right? Okay, good. Yes, thank you, Jim, for the introduction, and thanks for the invitation to speak to this just fascinating group. I've really enjoyed the morning, and it's great to be here and learn more firsthand about this organization that I've been sort of following off to the side a bit for a few years, wondering initially what exactly you were about, and I certainly understand that a lot better now. So anyway, the challenge before us is well, let me back up just a minute. I was asked to share with you what I see as the journey we've gone through in nutrient management during my career, and then talk a little bit about where we need to go in the future. And I need to remind you that my own personal historical perspective on this is certainly biased by my own experiences within the university system early on, and more recently with the Institute or its predecessor. So keep that in mind. This is one person's view of this historical perspective. And many of you are going to be aware of much of what we talk about, but I suspect there'll be pieces that will be new. And so this is our roadmap. We're going to try to do 35 years in 25 minutes. We'll start by looking at agronomic changes, because I think that's essential to understand nutrient management, because it provides us a context. And we'll talk about nutrient management, and then we'll spend a few minutes talking about where do we go from here. Now, I think it's important also to remember what life was like back in 1982. That's where this story begins, right? Well, what was it like? Well, that was the state of the art of personal computing. That's an IBM XT, no hard drive, two 5¼ drives, DOS 3.2, a monochrome monitor. I loved this machine. You can see I still have it. It sits in our porch on our farm home, and I've never been able to get rid of it. It was a time when Bill Gates had become a very wealthy man because of his development of a computer language for the common person, right? The commercial cell phone was just introduced. Can you imagine life without a cell phone? Well, prior to 1982, that was it. E.T. was trying to find his way home. Diet Coke was introduced to the world. Ronald Reagan was our president, and interestingly enough at that time, politicians on the far opposite sides of the aisle seemed to actually get along and communicate with each other, right? So it was a different time. All right, so now where were we in agronomy? Well, our focus was clearly on yield at that time. There was a big push in the research and extension community on maximum yields, on maximum yield research. We had investigators like Roy Flannery at Rutgers or Sterling Olson with ARS in Colorado that were doing maximum research, maximum yield research, throwing away any concern about economics or losses or efficiency and saying, what can we produce? What's the highest yield we can produce in a given area? We had farmers that were experimenting at a larger scale with that same question. Herman Warsaw was a farmer in Illinois, grew over 23 tons per hectare back in 1982. And so, or in 86, 87, I guess it was. And so the focus was on yield. How do we feed the world? How do we make more money? That was really the sense of things, right? And it contributed to a long-term increase in yields, I think, over time. This is corn yields from 1965 on to 2015. And you see that slope is about just a little less than 2 bushels per acre per year, 113 kilograms per hectare. And you look at where we were in the early 1980s, we're about at 100 bushels. And so it was a far reach from the 300 bushel plus or 23 ton that we were just looking at. Now, one of the most impressive visuals I ever encountered was when Ken Kasman at University of Nebraska took this very simple graph and reminded us of all the technology development and adoption that had to take place just to keep us on that straight line of yield increases. And so it was an era, a point in time when the focus was on yield and how do we produce yields higher and higher, and that has driven the system. I think some of that basic knowledge of system interactions, that has driven us over quite a long period of time. But it wasn't long before things shifted into a different theme, and it had to do with profitability. It was going from maximum yield research to maximum, what was called at the time, maximum economic yield, where profit was maximized, not just yield. We had conferences going on, we had workshops, we had farmers gathering together in clubs to talk about how do we become more profitable? How do we become more efficient? That was part of it as well. They would share records, there was software developed to just, it seems very, very simple spreadsheets now, but back in those days it was very creative, very innovative, just to allow farmers to quickly understand what their profitability was and to simulate practice changes and what impact that might have. So MEY, maximum economic yield. The next theme that seemed to appear was best management practices. It was a time where now our goals, our concerns have broadened some. And it wasn't just about productivity, but something at the time that was called environmental advantage entered the picture. And we saw the rhetoric, including the pillars of sustainability for about the first time: social, environmental, and economic. And this all became part of the dialogue of the day. In the Institute, we produced a series of fact sheets called BMP fact sheets that focused on specific cropping systems within specific regions. And in all cases, they would talk about the agronomic reasons for introducing this practice, but then also talk about, again, using the terminology of the day, the environmental advantage associated with this. So it was a significant broadening of the discussions and of the concerns of the time. Well, that very quickly led us to site-specific management, because even though those BMPs were based on science-based general principles, the practices that allow you to employ those principles in a particular site varied from site to site. So there was a recognition that you needed to deal with the variability among regions, among farms, and even within fields within farms. And so we started talking about this concept of site-specific management. At the same time, a program called the Certified Crop Advisor Program was introduced by the American Society of Agronomy. And this was partly in response, I believe, to the recognition that this was not simple stuff. This involved a lot of integration of the existing science and the real world on farms in order to define what practices were actually best at a specific location with the specific constraints at that location. And so this was a program that certified professionals working in agronomy, and exists today and includes about 13,000 folks, mostly in the US and Canada and a couple of other countries. Well, the next step in this evolution was what happened when this recognition of a need to be site-specific met advanced technology, and we called it precision agriculture. The visual that you see here was developed early on in this stage by Institute staff, actually, to illustrate what precision agriculture was about. And if you actually, it's interesting, all these years later, 20 years later, you go in and if you Google precision agriculture images, this still shows up as one of the first images or towards the top of the page anyway. During the same period of time, we saw a real focus on conservation tillage, no-till. And actually, Sally, it was the first round of soil, we called it soil quality at the time, but there was a lot of interest in soil good recognition of the importance of soil and its quality in meeting the needs of society. And we had lots of arguments. There were some of them academic. I think maybe we didn't emphasize the biology of soils quite as much in that round as we do today in our soil health discussions, but it was there. We saw no-till increase to 24% of the cropland in the US, 56% in Canada, and that all resulted in a 40% reduction in soil erosion. So that was one of the major accomplishments during this period of time. We did do a better job of protecting that soil resources. We still have too much erosion. We've got a lot of work to do, but we have made progress on this important challenge. Okay, that's a whirlwind through those 35 years of agronomy. Now let's zero in a bit more on nutrient management. And we'll start this by just looking at a general picture of fertilizer use, right? And you see nitrogen in green, and then phosphorus blue, and potassium in red. And a couple things I'll point out. One, you'll notice when we get into that early 1980s period, you'll see the slope of that fertilizer nitrogen use curve starting to drop. I mean, it was still climbing, but not climbing at the very high rate that it did prior to the 1980s. You look at the red and the blue lines, the P and K lines, they all pretty much followed they both followed basically the same pattern of a plateau. And so we've gone through several decades with really no increase in phosphorus use or potassium use in the US. And I'll remind you that during that same period, we had substantial increases in productivity. 50% increase in corn yields over the last 30 years of this period. And so you can see what was likely to be happening with nutrient use efficiency as we express it in terms of partial nutrient balance. And that's what you see in this table. Two different forms. A removal to use ratio, and then removal here is removal in the harvested portion of the crop. Use would be fertilizer used plus recoverable manure nutrients based on the system that NRCS has been using to define recoverability of manure. And then a balance, which would be, instead of a ratio, just the difference between removal and use. And so during this period, we basically held our own on removal to use ratios. The net balance increased a little bit, but we're producing a whole lot more. And actually, during that same period of time, we went from a period where we were mining nitrogen from soil organic matter like crazy, to a point where now in significant regions of the country, we're actually starting to rebuild soil organic matter, and then along with that, soil organic N. So you've got some N that's staying in the soil system, and still the numbers don't look too bad on removal to use. That's a positive story, I think. Then if we look at phosphorus, we see some truly remarkable removal to use values in my view. You see that ratio being 0.92, 92%. Of what we measure as being used is actually being removed in the harvested portion of crops. That's a pretty high ratio, right? So let's drill down a bit further on that, and we'll focus in on phosphorus. I'm going to change the scale on us. From a national level, we're going to zero in onto a few hand-picked states. Montana, North Dakota, South Dakota, and Minnesota. And I picked those states because they are states where, if you look at our best estimates of phosphorus removal and our best estimates of phosphorus use, they come pretty close to 1. All right? So then we can look at what happens to soil P levels when use and removal are about the same. And if you look at these numbers across our sampling periods, these are summaries that the Institute worked with the private and public laboratories across the US to generate. You'll notice that those numbers are either about holding the same or they're actually increasing a bit. What's the lesson there? Well, the lesson is simply that in soils like this, if we replace what we remove, soil P tends to stay constant, at least the soil P we measure with our routine soil test procedures. So this speaks very highly of the system level efficiency in these areas. Now, of course, as we saw earlier this morning, all soils of the world are not going to behave like this. But many of the soils, these beautiful soils that we have across much of the agricultural regions of North America, many of those soils do respond like this. They are pretty forgiving relative to phosphorus. But the story is about to change when we change our scale. Because our next step is to go down to a watershed level, all right? And we're gonna, and I've picked 2 watersheds again to illustrate the challenge. And everyone in this room is very aware of this or you wouldn't be here today, all right? And so we're gonna look at a watershed in northern Illinois and another one in eastern North Carolina, all right? And we're looking at the lower rock in Illinois and the black, those of you that are from North Carolina, this is the black watershed in North Carolina. And we'll look at fertilizer, recoverable manure, crop removal, and then a net balance. And so if you look at the fertilizer figure, these 2 are experiencing about the same amount of fertilizer use, but look at the recoverable manure. Okay? And then look at the crop removal, a little bit higher in Illinois as you probably expect, and then the net balance. We have a negative number in that Illinois watershed and a very, very positive number, of course, in North Carolina where we're growing lots of poultry and lots of hogs. And so if we do the math on that, we get the total numbers. And then if we look at soil P levels, we see just what we'd expect. In Illinois, you have very few soils that are in that extremely high P range, and and then you look at in North Carolina, you see quite a high number, and then it's just flipped around when you look at those that are testing low in P. No surprises here. And so what is this telling us? Well, this is the problem that you're all trying to help us with, and that is the issue that results from the decoupling of livestock and crop production. Nothing new there. And that's why it's so exciting, and I've had a few visits just this morning with manure processing technology that maybe is going to help us solve this problem of producing nutrients from manure that are transportable, spreadable, and cost effective. We seem to be making significant progress there, and that is what it's going to take in order to really fix the most serious in-field phosphorus deficiency problems in North America. So it's great to see that. So until that technology becomes available across farms, what are we doing? Well, our emphasis has generally been on preaching, if you will, about nutrient balance. And we use a couple of tools to do that. One is called NUGIS, the Nutrient Use Geographic Information System, a crude model that we developed, and I've been using this to generate some of these data here that we've been looking at over some of these past slides. And this model itself just works at a state, county, or watershed level. But we use that to try to get farmers to pay attention to their own nutrient balances, and then we have tools to help them do nutrient balance calculations themselves, to look at what's going onto the farm, what's coming off the farm. And then the soil test summaries that we when I say we, it's IPNI, that they work with the private and public laboratories to pull together so that we know where is our soil fertility at today, what direction is it going, and do that. We can only do it on a state level because of a number of reasons. But again, it calls attention to this issue of nutrient balance and trying to optimize this critical input. We're grateful to see an increase in use of soil testing. This is our estimate of the amount of soil testing that's been done in the U.S. Over the period you see in the slide, and you'll notice over the last 10 years, the number of soil samples collected in the U.S. has increased from less than 3 million to over 10 million, or around 10 million samples. Now, a lot of that has been driven by the introduction of precision agriculture, where you have to take more samples from fields. But I think it is also an increased awareness of the need for measurement. And I think it's pretty safe to say that nutrient use has never been as measurement guided as it is today. And I think that is real progress for us. It's not just we'll do what we did last year, but let's see what the numbers tell us, suggest might be the right thing to do. Now, if you want to experience sort of a case study of the application of nutrient balance principles into dealing with water quality issues, I'd recommend listening to Heidi Peterson's webinar that was recorded. She did that last month. Does a very nice job of putting this whole story together in a watershed in Minnesota. Okay, so what you see in the yellow box here is the way I described the various themes and progression of agronomic change and nutrient management in the past. And if I were to ask you, what are we focusing on? What is the theme of today? What do you suppose I would say? Sally, what would I say?
Soil health.
Okay, close. You really meant for our nutrient stewardship, right? Yeah, okay. That is what at least from the Institute's perspective, and I think much of the fertilizer industry's perspective, and a growing number of research and extension folks, this is what we need to focus on. And what is it? It's a global framework for nutrient BMPs within well-managed systems. It's applying the right nutrient source at the right rate, right time, and right place. Now, so far, there's nothing all that new or different about it. But what gets new and different is this last bullet, where right is determined by the impact on sustainability performance, where you look at all those parameters, metrics on the outside of that ring. That's what we're talking about. So for the first time, remember I indicated that one of the steps forward was understanding it's not just about productivity, but it's also about environmental impact. That was one step in this direction. But then there's a whole host of other factors that are involved as well. And what 4R nutrient stewardship does is it broadens that thinking out. And in our goal is to get the producer, get the farmer, to be thinking about all those performance indicators when practice decisions are being made on the farm. And that is quite a different concept. We're not there yet, but it's a solid concept that I think holds promise. And one of the reasons it holds promise, I think, is because of technology. Like you, Sally, I like technology. I think, appropriately applied, it can do marvelous things. We've talked about the changes in genetics. We can control the seedling environment to a degree that we've never been able to do. Amazing what we can do in the environment with equipment and fertilizer technology today. We have sampling equipment, soil sensing equipment, plant sensing capability that is amazing. And we have software that are decision support tools where a farmer and probably a consultant work together, and they bring together with this decision support tool our scientific understanding about how nutrients work in the environment and in the field, and then connect that to real-time weather conditions and say, all right, we don't follow a recipe that stays constant across farms or time, but we think at this location, in this particular season, this is the right thing to do. And that's major progress, that kind of integrating ability. We've got application technology that's much improved, and over time we've continued to increase our yield measuring and mapping capability. And then finally, and this gets us back, I didn't know that this would happen, but gets us back to our exercise we just completed over just before lunch. And that has to do with the illustration I'm using is something called Safe Tracers, which is a DNA-based traceability technology. I don't know much about it. I just started reading about it just recently, but it's a product that you spray on most anything. It's completely edible. It's the sequence is based on the same sequence that DNA uses, but what it does is that you get this little pocket, this little kit that allows you to take a swab off the apple, or maybe out of a fertilizer sample. That's how I got into this, was that this is technology they're talking about applying to fertilizer, and then you run it through the detector and it takes you back to, if it's fertilizer, where did the fertilizer come from, and if it's an apple, what orchard did it come from, and how, and then you use the technology that deals with ledger data, and you bring up that ledger, and all of a sudden we've got the consumer connected with the producer, with the farmer. Amazing technology. And anyway, I see that driving this whole picture, and as something that will accelerate the adoption of sustainable practices. And so to me, it's just an exciting time right now. The thing, though, that I wanted to emphasize moving into the last section of this presentation is that all of these technologies either require calibration data or data synthesis for appropriate use and to inform stakeholders. It comes to data. And that takes us then to this last section on where from here. And I want to start this with a quote from a computer scientist, Alan Kay. He said, "The best way to predict the future is to create it." And it sounds simple, but I think that is a powerful thing to keep in mind, that we can influence, of course, the future. And I want to now remind you of what this alliance is about. It says that its mission is to be North America's central forum and advocate for the sustainable use, recovery, and recycling of phosphorus in the food system. Well, my remarks here have really been just on one aspect of that mission, and what happens within the confines of farm fields. This is a much broader mission than that, obviously, and that most of you are involved in some other aspect of this, but I think it's critical that you understand this within field aspect as well. But what I want to call your attention to is that central forum. Jim, I think that's a huge challenge. It's a huge challenge because you're talking about a very diverse group that needs to be engaged and needs to be collaborative in order for this to actually happen. And that's a challenge because of the complexity of the phosphorus cycle and for a lot of reasons. And that leads us to what many call evidence-based science. Viewing data as a primary product of science that grows in value with accessibility and with time, seeing each new research contribution as a continuation of the discovery process, not just as an independent event, so metadata become terribly critical. It involves things like data set publishing, data repositories, systematic reviews, meta-analysis, etc. It's about data. We've heard many times this morning already about data and its importance. Well, what this does is it says, let's remember that all the way through the process, and remember that data is what we really need to pay attention to. I think one of the best examples I've ever seen of the power of this approach comes oddly enough to us from the world of theoretical physics. And in case you haven't been following the story of gravitational waves and their measurement, these are distortions in space-time resulting from huge shifts in mass somewhere in the universe, predicted by Einstein in 1916 as part of his general theory of relativity. Well, lo and behold, in September of 2015, at two places in the US, the impact on space-time was measured on Earth. And according to the world of physics, showing that Einstein 100 years ago was actually right. Now, I was at the annual meeting when this paper was reviewed, and it just stunned the whole audience. They said, "Oh, wow, I mean, this is amazing." And actually, science declared it the 2018 breakthrough of the year, and this discovery did, in fact, win the lead researchers the Nobel Prize in Physics in 2017. Pretty big deal. Okay, Paul, so what does this have to do with us today? Huh? Well, I think there are two lessons that are here to absorb. One was actually brought a week later after that original paper was published in Science, where an editor reviewed the history of the search for gravitational waves. And what that editor did was remind us that this was not a singular event. This was just one step in a long series of events that built on one another that eventually made this huge discovery. And so it tells us that science progresses incrementally. Each contribution needs to connect to the past and to the future, and each viewed as part of the whole. That's lesson one, right? Lesson two actually results from the nature of that original 2015 article itself, and that is that it had 1,000 authors. It took almost 3 pages of the journal just to list the authors.
Is Einstein on there?
No, they didn't include him. And so what's the message here? Well, you had 1,000 authors collaborating, sharing ideas, sharing a lot of resources, and sharing data. It again illustrates the power of working together at a data level. And so lesson one of Einstein's lessons for the Sustainable P Alliance, if you will. Lesson one, science advances incrementally, studies need to connect. And we need to remember that when we publish so that we have those connectors in place. Collaboration and data sharing are powerful. And so you might have noticed that I just retired like 7 months ago or so. And so it's been a new experience for me. I've never done this before. And so one of the things I've noticed is that it's when an institutional mission gets replaced by a personal mission. An institutional mission, something that's defined by a broader group of some sort, and then it becomes personal, where you integrate your professional life with your personal life and everything else, and you hang on to the professional life that you think is most important. Well, this data stewardship and evidence-based science has become part of my own personal mission. It's one of the reasons why I accepted the invitation, Jim, to come and try to emphasize this point with this particular group, which I thought could benefit from remembering the importance of the data you do. And so, in closing, remember your mission, and my advice, take it or leave it, of course, is that you view shared accessible data as a primary output of your efforts and an avenue for increased collaboration in a non-competitive space, yes, probably, and that evidence-based management of the P cycle is a great target for this group to have. And with that, I apologize for introducing an otherwise wonderful lunch, and thank you again for the invitation, Jim.
Thank you. Thanks for that, Paul. It was truly entertaining for a bunch of geeks. Absolutely great entertainment at lunchtime. And I think within our research coordination network, your advice, we tried very much to keep in the spirit of that.
I can see that.
We brought together a lot of diverse folks and produced data sets that are out there available and improving and such as Steve Powers, for example. He's a major driver behind a lot of those analyses, for example. So the floor is open for a few questions before we take another social period before we start the afternoon.
Yep.
I'm interested in a little more on the information about the Blackwater watershed area.
Right.
How up to date is that information? And do you know if the situation there is improving or getting worse with that?
That specific watershed, I did not look at a temporal change, but in most cases, things are getting better. There is an educational effort that has been at least partially successful, and there's a recognition that there are problems there, and more people, even in the Black River watershed, there are still areas that are getting insufficient levels of phosphorus. And so I think what we're seeing is farmers are being a bit more interactive in moving nutrients around a bit. But it's a slow process. These are not easy solutions to implement, and we need, again, some new technology before that's going to happen. Yep.
Hi. Just a general question. I have heard already a few times people mentioning CRISPR-Cas, which will allow us to use more efficiently genetic diversity than we did before. But so far, nobody has mentioned the plant microbiome, which has not been effectively manipulated and has a lot of potential to be a major player in plant nutrition.
Yeah, I couldn't agree with you more. There's so much exciting methodology development in that realm that's going to allow us to learn a lot more about fine-tuning, as you were talking about in your presentation, the system and trying to get to right more frequently than we are. A great amount of activity in that area right now, and some of it is being driven by the soil health movement, where we're greater emphasis on biology, and I think we're going to make great progress in that area because of partly what's going on in general genomics and the genetic tools available that we never, the soil microbiology was just a mess in the past because of its complexity. We're making progress there. So who knows where that's going to take us, but it's likely to be a productive area in my mind. Yeah. It doesn't move us away, in my view, though, of the mass balance kinds of challenges we have. You know, for a system to be sustainable, I don't care what you do with the recyclers in the system, the microorganisms. You may be able to move thresholds down. In other words, you reduce the amount of total P that needs to be in the system to meet needs, but at some point it is a matter of replacing what gets removed, or you have a sustainability issue at some point.
Well, thanks for a wonderful talk, really inspirational. My question is 2020 hindsight. That's what we typically have, looking back 35 years. What are the critical junctures where you think we could have done things differently and could have advanced more quickly? So what are the dead ends that we explored?
Interesting question. Yeah. You know, I think it's in hindsight, it seems we could have gotten to many of these transition points faster. And I guess in my own biased view of what's important in the future, and that's back to this evidence-based science, I think if we would have stayed closer to our data 30, 40 years ago and actually looked at and we're real and honest and transparent with how good our recommendations for practices were at the time, and they were not very good. I mean, if you looked at our what we were telling farmers, here's your soil test, here's your soil test, and you should apply, 35.6 kilograms of hectare. I mean, that's the kind of stuff we were doing. And if you looked at the actual accuracy of that system, not much the accuracy, but the uncertainty, it was a huge amount of uncertainty. And we kept that sort of hidden from the end user. And I have to admit, I go back and look at my notes when I was teaching undergraduate soil fertility classes back in the 1980s. And I'm a little embarrassed. Because what did I show? I didn't show the scatter of the real world. I would show this nice curvilinear, line, and I'm afraid what I taught was the students expected, to be able to come up with a 35.6 recommendations. Yeah, well, it's right there. Here's the X and there's the Y. That's what we do. Well, we were not as transparent as we could have been with those systems. And I think if we would have been more evidence-based back in those days, we would have progressed faster. We said, we need to do better than this. And, it served us well at the time, but it slowed down progress. Well, thank you very much for your patience.
Big hand for Paul.